So now that we have discussed how to represent preferences and how to discuss the budget line, we can actually put these two together and look at how an optimal choice would look like. So we have in this diagram the mean return on the y-axis, the standard deviation of return on the x-axis. We have the indifference curves. We have discussed what is the slope of these indifference curves. We also have the budget lines, and we have found that the slope of the budget line is given by this expression. So as usual, the optimal point is going to lie at a tangency point. So where the slopes of the budget line and the indifference curves become equal. And that would be the most preferred risk return combination. So from here, we can figure out what's the mean rate of return that this person would like to choose given the trade-offs involved, and what's the standard deviation of return, right? And you can use those information to back out what will be the fraction of the wealth that is going to be allocated to the risky asset, and what's the remaining fraction that is going to be allocated to the risk-free asset. So that's how you would solve the problem. So let's now think about a few different aspects related to this. So imagine now that compared to the previous risky asset, there is a new risky asset that appears, and the consumer has to decide about which risky asset would he prefer to have in his portfolio. So there's a choice of either involve the original risky asset versus involving the new risky asset. And just to make things simpler for us, let's assume that the new risky asset is such that it's the expected rate of return is higher, but its standard deviation is also higher, right? If you did not have this scenario, so for example, suppose the new risky asset had a higher rate of mean rate of return and a lower standard deviation, then clearly that one would be preferred, right? So in order to make things interesting, let's suppose that it has higher risk as well as higher standard deviation. So let us also assume that this inequality is satisfied, that Ry minus Rf by sigma y is strictly greater than this. If this was not the case, we would just do the same analysis, but we would just interchange the two risky assets, right? So what does this tell us, this Ry minus Rf by sigma y? So remember that in both the cases, you're going to actually have the intercept as being the same, right? And this is independent of what the returns or the standard deviation of these risky assets are, right? So the intercept is given by the risk-free rate, right? So what this is telling you is that basically we are assuming that the new asset has a higher slope compared to the previous one, right? And this is the analysis that we had for initially. This was the situation that at the optimal point, this was the value of X was being chosen for the old risky asset, where you ended up with the mean rate of return of Rx and the new rate sigma X. Now, this is the new budget line. How do we know that it's going to lie above the previous budget line? Because we know that the intercept is the same, the RF, right? And we, by our assumption, we have that the slope is higher, right, for the new asset. And so therefore you end up with the budget line lying above. So what that means is that the consumers would prefer to have the new budget line, but subject to a very important caveat. This assumes that basically you are free to allocate your wealth in any fraction between 0 and 1, right? Between the risky asset and the risk-free asset, right? So if that is the case, we see from this diagram that you end up on a higher indifference curve. Remember, the more to the northwest we are going, the better off you are. So therefore, this is corresponding to a higher indifference curve. Why the other way of seeing it is that for the same value of sigma, you get a higher mean return, right? So that's why this new indifference curve is better, right? Now, why did I say that this is an important assumption that we are making, that you are free to allocate any fraction between 0 and 1 among the risky asset and the risk-free asset? Because suppose that was not the case, then we could have well had a situation where you would have had an indifference curve which passes through this point. Remember, this is the extreme case where you're putting all your money in the risky asset. and that could have been on a higher indifference curve compared to if you have put all your um, wealth in the risky asset in the for the new risky asset, right? So we implicitly assume that you are free to choose x between 0 and 1, and it's not a case of choosing x equal to 1 and comparing the two risky assets, right? Okay, so that's one point to note. The other thing to note is to think a bit more broadly about how risky is an asset. So far we have been using the standard deviation as a measure of the riskiness of an asset, right? So for risk-free asset, standard deviation was equal to 0, so there was no risk. And for the other asset that we had in our analysis, because we were dealing with two assets only, then we thought of using the standard deviation or equivalently the variance as a measure of the risk of the asset, right? Now, if you have multiple risky assets, then we need to think a bit deeper. And this is something that we are going to think about in the future as well. But the reason is because the asset's value actually now starts depending on the other assets' values as well, right? So let's think of an example. Suppose that initially you had asset A whose value was 10 with probability half and minus 5 with probability half. Then in that case, if you were a risk-averse person and you had to decide just to buy asset A, then you are not going to be paying more than 2.5 for an asset A, right? And in fact, if you are risk averse in the sense that you kind of do not go by just the expected value, then we can kind of like go through our analysis and argue that 2.5 is the most you are going to pay. And if you are strictly risk averse, then you are definitely going to be paying less than 2.5, right, for this asset. Let's consider another asset B, which also has a payoff of 10 with probability half and minus 5 with probability half. So again, you are not going to be paying more than 2.5 for this asset B. But this asset B has a particular characteristic, right? So this asset B has the characteristic that it's going to take a value of minus 5 when asset A takes a value of 10, and it's going to take a value of 10 when asset A is 10 to take a value of minus 5. Now, if you can combine these two assets and purchase them together, what you observe is that this is going to give you a sure return of 5, right? Why is that the case? Because in the state in which asset A's value is going to be 10, assets B value is going to be exactly minus 5, right? So if you have both of these assets in your portfolio in equal share, then you know that you are going to get a value of 5 uh, in this state, right? And similarly, in the other state, you have got a value of minus 5 for asset A and a value of 10 for asset B. So again, if you add up, you get a value of 5 again, right? So you have basically, by combining the two assets, you have basically made a risk-free asset, right? And so in that case, you would be willing to purchase both the assets by paying a price of 5, which is more than what you would have paid if you were to individually think about how much you were willing to pay for each of these assets in isolation, right? So what that tells you is that this is an illustration of the fact that value of an asset will in general depend on how it is correlated with other assets. And typically assets that move in opposite directions, let's say with respect to the stock market, these are often valuable because they actually help to reduce the overall risk, right? And the value of an asset depends not just on the variance or the standard deviation of its own returns, but it also depends on the correlation of its return with other assets. And oftentimes, this correlation aspect turns out to be more important in characterizing risk related to an asset rather than the variance. So the important takeaway from our discussion here is that the amount of risk in an asset depends also on its correlation with the other assets. So we can also think of actually quantifying this amount of risk. So how should we think about now the risk in an asset? So one way of doing it is to think about how risky is an asset compared to, let's say, the stock market overall. Okay. So let's denote by beta the riskiness of a stock relative to the risk of the market. So this is the ratio of risk of asset I as a fraction of the risk of the whole market. And this measure is often known as beta of a stock. Okay. So it's not just that we are using the Greek letter beta. So when you hear what is the beta of a particular financial security, so that this is what we are talking about. Okay. So there's also expression for this ratio. So if you kind of like do the calculation, and we might see it at some point later, is that this is nothing but the covariance of Ri and Rm divided by the variance of Rm, where Ri is the rate of return of asset I, Rm is the market's rate of return. Okay, so this fraction is exactly the value for beta I. And let's see what is the implication of this for thinking about what would be the equilibrium rate of return for any asset. So remember, we had discussed this before when we were thinking about decision of buying assets in the world in which there was no uncertainty, right? So if you recall, we had this result that in a world without any uncertainty, the rate of return from all the different assets that people hold has to be the same, right? Now, once you start incorporating uncertainty in the analysis, the statement needs to be modified a bit, right? So the statement needs to now say that all the assets that you have, their risk adjusted rates of return must be equal, right? So because now you've got some assets which are more risky or less risky compared to the others. So you need to think about what does that imply for the rates of return, and then you need to adjust those risks and then look at the rates of return and then say that, okay, once you have adequately adjusted for those risks, then the rates of return must be equal, right? So, of course, the big question is how do you adjust for this riskiness? So we use this notion of beta and the price of risk that we have discussed so far. So recall that the riskiness of an asset I, we can think of that relative to the total market risk as this beta I. Okay. Now the total market risk from here is sigma m. You can also see it, by the way, from this other analysis, but that is fine. So just in terms of the notation that we had, recall that we are thinking of the sigma m as the market risk. And so therefore, you end up that the total riskiness of an asset is equal to beta I times sigma m. How do you get this? So this is the definition of beta I that we had, risk of asset I by risk of whole market. We are saying that the risk of whole market, think of that as the standard deviation of the rate of return of the market. And so therefore, the risk of asset I is beta I times sigma m. Okay. All right. So now next we need to think about the price of this risk. And this is basically the slope of the budget line that we had discussed before. So that's equal to Rm minus Rf by sigma m. So this is the same expression that we had got here when we were looking at the budget line slope. The only thing is that now we are thinking of this risky asset as the overall stock market portfolio, right? So therefore, the slope that we had, which was the price of the risk, now the M corresponds to the market portfolio, basically. And so therefore, we end up with Rm minus Rf by sigma M as the price of the risk. And that is what, this is the total risk. This is the price. And so therefore, the cost of this risk is this price multiplied by the total amount of risk. And so therefore, that's equal to P into beta I into sigma M. Now, if we plug in this expression of P that we have here, which is the slope, remember, of the budget line when you have got the risky asset as the overall stock market, then we end up with Rm minus Rf by sigma M. So the two sigma M's cancel out. And so you end up with beta I times Rm minus Rf, right? So this is the risk adjustment term for asset I. So this was the rate of return of asset I. So the risk adjusted rate of return is Ri minus beta I times Rm minus Rf, right? Okay. So how does that help us? Because we actually know what the value of beta is for a risk-free asset. How do we know what is the value for the risk-free asset? Remember, this is the definition of beta. So if you have a risk-free asset, so that's going to always take a constant rate of return. And so therefore, the covariance of that with the market risk has to be zero, right? And so therefore, for a risk-free asset, the value of beta is equal to zero. And so therefore, what is the risk-adjusted rate of return for a risk-free asset? It's just equal to the risk-free rate, right? Why is that the case? Because there is no risk in a risk-free asset. And so therefore, we do not need to adjust for the risk, right? This is the risk-adjusted rate of return for any particular asset I. This has to be equal to Rf, right? Which is the risk-adjusted rate of return for the risk-free asset. And so therefore, we have that Ri minus beta I times Rm minus Rf is equal to Rf. And rearranging it, we get an expression for in equilibrium, what's going to be the expected return on any asset. So the expected return on any asset must be equal to the risk-free return plus the risk adjustment term that we had derived, right? Why do we need this risk adjustment term? Because this basically reflects the extra return that people demand in order to bear the risk that the asset has. So notice one thing, that this can actually be something which can be actually higher or lower than the risk-free rate, right? Depending on the sign of this beta I. So RM clearly is more than RF, as you would expect, but beta I can be something which can be positive or negative, and so therefore RI can be more or less than the RF, right? So this equation actually we'll see is also the main result of what is known as the capital asset pricing model, and this is something that we will discuss in much more detail in coming weeks, right? So this is just our first glimpse, but we'll come back to this equation and discuss it in a bit more detail and think about what does it mean about what is the market portfolio and how to interpret this equation, and more importantly, how to use this equation, right? So that is something that will come up in the next few weeks. And so again, the reference for this discussion of this risky asset is this book on microeconomics by Halverian that we have been using in our discussion so far. So if you are interested in looking at some other aspects related to this analysis, that is a place where you can look at things.